Hello and welcome to Math Zone African Motives, your go-to channel for Electrotechnics N4 nated engineering. Today, we're diving into the fundamental ways resistors are connected in a circuit. Understanding these connections is crucial for analyzing and designing any electrical system. By the end of this lesson, you will be able to identify, analyze, and calculate key electrical quantities in series, parallel, and series parallel circuits. There are three primary methods to connect resistors: in series, in parallel, or a combination of the two, called series parallel. Let's begin with the first type, resistors connected in series. Our first topic is resistors connected in series. In a series circuit, resistors are connected end to end, forming a single path for the current to flow. Let's look at a simple diagram showing three resistors in series with a battery. Notice the current, labeled I total, flows out of the battery's positive terminal through each resistor in turn and then back to the negative terminal. A key characteristic of a series circuit is that the current is the same through every component. This means I total is equal to I1, which is equal to I2, and so on. The current has no other path to take. Second, the total voltage from the source is divided among the resistors. This is why a series circuit is often called a voltage divider. The sum of the voltage drops across each resistor must equal the total supply voltage. Finally, let's derive the formula for total resistance in a series circuit. We start with the voltage relationship. We know V total equals the sum of the individual voltage drops. According to Ohm's law, voltage is current times resistance. So we can replace each voltage term. Since the current is the same everywhere in a series circuit, I1, I2, and I3 are all equal to I total. We can factor I total out of the right side of the equation. Now we can divide both sides by I total to find our final formula. The total resistance in a series circuit is simply the sum of all the individual resistances. It's a straightforward addition. It's time for our first worked example to put these concepts into practice. Here's the problem. A series circuit has three resistors of 25, 42, and 60 ohms, connected to a 200-volt DC supply. We need to calculate several quantities. Remember the exam tip we saw? Let's start by drawing a labeled circuit diagram. Drawing this diagram helps organize the problem and visualize the components and known values. Now, let's list our given values to keep everything clear. Let's tackle each part of the problem. First, the total resistance. We use our new series formula. The total resistance is the sum of the three resistors, which gives us 127 ohms. Simple addition. Next, the total current. Now that we have the total voltage and the total resistance, we can use Ohm's law. Dividing 200 volts by 127 ohms gives us a total current of approximately 1.575 amperes. This is the current drawn from the supply. For part C, the current through each resistor, it's a trick question. We know that current is the same everywhere in a series circuit. So, the current I1, I2, and I3 are all equal to the total current we just calculated, 1.575 amperes. Part D asks for the voltage drop across each resistor. Again, we use Ohm's law, but this time for each individual resistor. For R1, it's I total times R1, which is about 39.38 volts. For R2, the drop is about 66.15 volts. And for R3, it's 94.5 volts. Notice that if you add these three voltage drops, they sum up to our total supply voltage of 200 volts. For the total power drawn from the supply, we have three formulas to choose from. Let's use the simplest one. P equals V times I. Total power is total voltage times total current. This gives us 315 watts. Remember, these different power formulas will all give you the same answer. Finally, the energy dissipated in 1 minute. Energy is power times time. First, convert 1 minute to 60 seconds. Then multiply our total power of 315 watts by 60 seconds to get 18,900 joules, or 18.9 kilojoules. So, in 1 minute, the entire circuit converts 18.9 kilojoules of electrical energy into other forms, mostly heat. Let's work through another problem to solidify our understanding of series circuits. This time, We'll start with slightly less information and use our formulas to find the missing values. Here's the scenario. A two-resistor series circuit has a total current of 5 amperes. We know the voltage drop across the first resistor is 100 volts, and the energy dissipated by the second resistor in 45 seconds is 40.5 kilojoules. Let's calculate the resistance of each resistor, the supply voltage, and the total power drawn from the supply. Let's list the information we have. This helps us focus on what we need to find. We need to find R1, R2, V total, and P total. It looks like we have enough information to start solving. For part A, let's find the resistance of each resistor. We know the total current is 5 amperes. Since it's a series circuit, this means the current through R1 and R2 is also 5 amperes. For R1, we know its current is 5 amperes and its voltage drop is 100 volts. Using Ohm's law, R1 equals V1 divided by I1, which is 100 over 5, giving us 20 ohms. Now for R2. We don't have its voltage, but we have information about energy. We know the energy dissipated is 4,500 joules over 45 seconds. We can use the formula that connects energy, current, and resistance. Rearranging this formula to solve for R2, we get Q2 divided by I2 squared times time. Plugging in our values for Q2, I2, and T, we calculate the resistance of R2 to be 36 ohms. Now for part B, the supply voltage, V total. We know that V total is the sum of the voltage drops across the resistors. We already have V1. We can find V2 using Ohm's law for R2. V2 is I2 times R2, which is 5 amperes times 36 ohms, or 180 volts. Adding V1 and V2 gives us the total supply voltage, which is 100 plus 180, or 280 volts. Finally, for part C, the total power drawn from the supply. We can use P equals V times I. The total power is the total voltage of 280 volts times the total current of 5 amperes, giving us 1400 watts. We've successfully used a variety of formulas to solve this series circuit problem. Now let's move on to our second method of connecting resistors. Parallel. Unlike a series connection, in a parallel circuit, the resistors are connected side by side across the same 2 points. This creates multiple paths for the current to flow. This fundamental difference leads to completely different rules for voltage and current. First, the voltage across each parallel branch is the same. It's equal to the total supply voltage. This is because each resistor is connected across the same 2 points, so they all see the same potential difference. Second, the total current from the source splits and flows down each branch. This is why a parallel circuit is often called a current divider. The total current is the sum of the currents flowing through each resistor. Let's derive the formula for total resistance in a parallel circuit. This one is a bit different. We start with the current relationship. I total equals the sum of the branch currents. We can replace each current with its Ohm's law equivalent, V over R. Now the crucial step. We know that the voltage is the same across all parallel components, so V total, V1, V2, and V3 are all equal. This means we can replace all the voltages with V total and then factor V total out of the right side. By dividing both sides by V total, we arrive at the formula. The reciprocal of the total resistance is equal to the sum of the reciprocals of the individual resistances. So, to find R total, you must calculate the sum of the reciprocals first, and then take the reciprocal of that sum. As an exam tip, it's often more convenient to find a common denominator and combine the fractions, as shown here. Let's work through an example of a parallel circuit. This problem provides a mix of current, energy, and power information. Here's the problem. We have 3 parallel resistors. We know the energy dissipated by R2 is 4250 joules in 25 seconds. We're given the currents for R2 and R3, and we're given the power drawn by R1. We need to find R2, the supply voltage, I1, the resistances of R1 and R3, and the total resistance. Again, let's list our given values to keep everything in order. We need to find a starting point. Let's look for a component where we have enough information to calculate something. For resistor R2, we know the current, the energy dissipated, and the time. This is perfect for calculating the resistance R2. We'll use the energy formula Q equals I squared RT and solve for R2. Plugging in the numbers, R2 is 4250 divided by 2.75 squared times 25. This gives us approximately 22.48 ohms. That's our first answer. Next, let's find the supply voltage, V total. In a parallel circuit, we know the total voltage is the same as the voltage across any branch. Since we just found R2 and we know I2, we can calculate V2 using Ohm's law. V2 equals I2 times R2, which is about 61.82 volts. This value is our supply voltage, V total. Now that we have the supply voltage, we can find the missing values for R1 and R3. Let's find the current I1. We know the power for R1 is 144 watts, and the voltage across it is the supply voltage, 61.82 volts. Using the power formula P equals V times I, we can find I1 by dividing 144 by 61.82, which is about 2.33 amperes. With the current and voltage for each resistor, we can now find their resistances. For R1, it's 61.82 volts divided by 2.33 amperes, or 26.53 ohms. For R3, it's 61.82 volts divided by 3.6 amperes, which is 17.12 ohms. Finally, let's calculate the total resistance of the circuit. We can do this in two ways. First, we can find the total current by adding the three branch currents, and then use Ohm's law. The second way is to use the reciprocal formula for parallel resistors, now that we have all three resistance values. Plugging them in gives us the same result, 7.12 ohms. Both methods are valid. Let's introduce a very useful concept for analyzing parallel circuits: the current divider rule. The current divider rule tells us how the total current entering a parallel junction is divided among the branches. It gives us a direct way to find any branch current without having to calculate the total voltage first. We can derive this rule from Ohm's law and the parallel circuit rules. Consider a simple two-resistor parallel circuit. We know V1 equals V2, which also equals V total. Using Ohm's law, I1 times R1 equals I2 times R2. So the branch currents are inversely proportional to their resistances. We also know that I total is the sum of I1 and I2. We can substitute our expression for I1 into this equation. After some algebraic manipulation, we can factor out I2 and solve for it. The result is the current divider rule for I2. Notice the numerators. The current I2 depends on the resistance of the other branch, R1. Similarly, the formula for I1 depends on R2. The rule is easy to remember. The current through one branch is equal to the resistance of the other branch divided by the sum of the two resistances, all multiplied by the total current. It's a quick shortcut. Let's apply the current divider rule with a practical example. In this circuit, we have two resistors, 20 ohms and 30 ohms in parallel. The total current is given as 8 amperes. Our goal is to find the current flowing through each resistor, I1 and I2. First, let's solve this using the method we learned earlier. We'll find the total resistance, then the voltage, and finally the branch currents. For two parallel resistors, the total resistance is their product divided by their sum. This gives us 12 ohms. Next, we find the total voltage, which is the voltage across each parallel resistor. Using Ohm's law, V total equals I total times R total, giving us 96 volts. Finally, we can find the branch currents. I1 is V total divided by R1, which is 4.8 amps. I2 is V total divided by R2, which is 3.2 amps. Now, let's solve the exact same problem using the current divider rule to see how much faster it can be. For I1, we use the formula with the other resistor's value, R2, in the numerator. That's 30 over 20 plus 30, all times the total current of 8 amps. This gives us 4.8 amps directly. For I2, we use R1 in the numerator. That's 20 over phi times 8 amps, which gives us 3.2 amps. As you can see, the current divider rule gets us the answer in fewer steps, which is very useful in exams. Our final connection type is the series parallel circuit. These circuits are a little more complex because they combine both series and parallel connections. Because they contain both types of connections, both current and voltage are divided within the same circuit. You have to be very careful to use the correct rule for each part of the circuit you are analyzing. There is a systematic procedure you should follow to analyze these circuits. First, always draw a clear diagram. You can't solve it if you can't see it. Second, label all your resistors. Third, indicate all currents and voltage drops with arrows and symbols. Fourth, note the supply voltage and total current. And finally, you solve the circuit by working from the inside out, or, more generally, by starting where you have the most information. A common strategy is to simplify the parallel sections into single equivalent resistors, making the whole circuit look like a simple series circuit. Let's work through an example to see how this works in practice. Here's the diagram. We have R1 and R2 in parallel, and this combination is in series with R3 and R4. Our goal is to find total resistance and all the individual currents. First, let's simplify the parallel part. We'll use the product over sum rule. The equivalent resistance for the parallel combination of R1 and R2 is 17.143 ohms. We call this R parallel. Now our circuit is just a simple series circuit. The total resistance is the sum of R parallel, R3, and R4. Adding these up, we get a total resistance of 55.143 ohms. This is the equivalent resistance of the entire circuit. Now that we have the total resistance for our series parallel circuit, let's find all the currents and voltages. This is where we need to work our way back through the circuit. We've already found the total resistance. Here's our diagram and our calculated total resistance. Let's start by finding the total current. We use Ohm's law for the entire circuit. V total divided by R total. 180 volts divided by 55.143 ohms gives us about 3.264 amperes. This is the current flowing from the supply and through the parts of the circuit that are in series with the supply. Looking at our diagram, this total current flows directly through resistor R3 and resistor R4. So I3 and I4 are both equal to 3.264 amperes. Notice we've already found two of our branch currents. Now we need to find the currents I1 and I2, which flow through the parallel branch. To do this, we first need to find the voltage across the parallel branch, which we'll call V parallel. We can find V parallel by using Ohm's law on the equivalent parallel resistor. The current through this equivalent resistor is the total current, 3.264 amperes, and its resistance is 17.143 ohms. Multiplying these gives us about 55.955 volts. This is the voltage across both R1 and R2. Now we have the voltage and resistance for both R1 and R2. We can use Ohm's law again to find their individual currents. I1 is V parallel divided by R1, which is 1.865 amps. And I2 is V parallel divided by R2, which is 1.399 amps. We have now found the current through every resistor in the circuit. Part C asks for the energy dissipated by the 40 ohm resistor, R2, in 3.5 minutes. First, convert 3.5 minutes to 210 seconds. Then, use the formula Q equals I squared RT. Make sure to use the current specific to R2, which is I2. Plugging in the values gives us 16,440 joules, or about 16.44 kilojoules. This example demonstrates the step-by-step process for solving complex series parallel circuits. Sometimes, circuit problems are presented in words, not diagrams. It's an important skill to be able to translate these descriptions into a proper circuit diagram. Let's work through two examples of drawing diagrams. The first example asks us to draw a kettle connected to a 240-volt supply and drawing 5 amperes. In electrical diagrams, we often represent real-world loads, like a kettle's heating element, as a simple resistor. So, we'll draw a voltage source, which is the 240-volt supply, and a resistor, which represents the kettle. Since the kettle is drawing current, the only way it can be connected is in a simple series loop. The current I total of 5 amperes flows from the supply, through the kettle's element, and back. This diagram correctly represents the description. Always remember that for exam purposes, a load like a kettle is simply drawn as a resistor. Now for our second example, an aluminum conductor and a copper conductor of the same length are connected in parallel, and together they carry a total current of 70 amperes. The key phrase here is connected in parallel. So we'll draw two parallel branches. The first branch will contain a resistor labeled Al, representing the resistance of the aluminum conductor. The current through it is IAl. The second branch will have a resistor labeled Q for copper with current IQ. The total current of 70 amperes flows into the junction where the branches split and out of the junction where they recombine. A voltage VAL equals VQ exists across both parallel conductors. We don't need to show a battery unless we're asked to. This diagram correctly shows a parallel connection carrying the total current. It's your turn to practice. Here's a problem for you to attempt. Pause the video here and try to solve this problem on your own. Remember to draw a diagram, list your given values, and apply the correct formulas. All right, let's go over the solution together. Compare your answers with mine. First, list your given values. Then draw your labeled circuit diagram. This is a series circuit. Question 1.1 asks for the total current. First, find the total resistance by adding the three resistors. That's 95 ohms. Then use Ohm's law for the whole circuit. Total current is 150 volts over 95 ohms, which is about 1.579 amperes. For question 1.2, the voltage drop across each resistor, remember that the current is the same in a series circuit. So, I1, I2, and I3 are all 1.579 amperes. Now use Ohm's law for each resistor. V1 is about 39.48 volts, V2 is about 47.37 volts, and V3 is about 63.16 volts. If you add these up, they should approximately equal 150 volts. Question 1.3. Energy in R3. Convert 1.8 minutes to 108 seconds. Use the formula Q equals I squared RT. Make sure to use the current through R3, which is 1.579A, and the resistance of R3, which is 40 ohms. The energy dissipated is about 10.74 kilojoules. Finally, question 1.4, total power drawn. Use P equals V times I for the whole circuit. Total power is 150 volts times 1.579 amperes, giving us about 236.85 watts. How did you do? If you made a mistake, go back and review the relevant section. Let's quickly recap what we've covered today. We started with three main ways to connect resistors. We learned that in a series circuit, current is the same everywhere, but voltage is divided. The total resistance is the sum of the individual resistances. In a parallel circuit, voltage is the same across each resistor, but the total current is divided among the branches. Total resistance is found by adding the reciprocals. We then combine these concepts to solve series parallel circuits, learning the importance of a systematic step-by-step approach. We also discovered the handy current divider rule as a shortcut for parallel circuits and practiced drawing diagrams from text descriptions. Remember, the key to success in circuit analysis is to understand the fundamental rules and practice applying them. You are now equipped with the knowledge to identify and solve a wide range of series and parallel circuits. Thank you for joining me on Math Zone African Motives. If you found this video helpful, please like and subscribe for more N4 engineering content. See you next time.